I'm going to introduce the paper QLIP, text-aligned visual tokenization that unifies auto-regression, multimodal understanding, and generation. So the motivation, like a very little quick motivation about the paper is that the observation that we sort of get from the NLP side. So basically, frontier large language models, they don't actually discriminate between generation or understanding. But for images, basically, or generally, like for vision, we kind of have this kind of separation of like image understanding or like image generation kind of in like two totally different directions and then two methodologies. So the goal here is trying to kind of figure out, is there a way that we can sort of like try to like combine these two and then sort of like everything like in a unified way. So that's actually the sort of the motivation of the work. So if we kind of go a little bit deep into the methodologies, so there are actually, as I just mentioned, there are like two like separate directions. One is like contrastive pre-training or like a QLIP, for example, which actually shows very good performance for language and image. And it also shows very like after these contrastive pre-training between text and the image pairs, the visual encoder actually can be used as a zero-shot vision representation extractor for a lot of like different downstream tasks. And this is pretty good for especially for understanding. But we never know that if this encoder is actually useful for like generation. And then actually there's like some previous work that try to do start from QLIP to do some generation, but like not very like a good result yet. And the other is like autoencoder or like a variational autoencoder. And here we like kind of think about like quantization-based autoencoder, where we have a encoder-decoder architecture, and between the encoder and the decoder, there's a quantization that discretize each feature that is after the encoder to a discrete index. And this is very popular in the domain of generation, where we want to have like a very faithful or like a photometric fidelity kind of image, which actually that reconstruct the image. And to train these two different models, then we have designed kind of different losses to like these different architectures. And so the idea here is they're very simple. So is there a way that we can actually bring them together? So basically here now we're gonna have a encoder decoder with the quantization in between. So for the we still have the autoencoder kind of architecture. And once we are like training this autoencoder, we also sort of have the like text image alignment loss. So we introduce a text encoder and we have a QLIP loss that aligns the text embedding together with image embedding. So in this case, we use a special classification token for each of the image so that it can like basically cross-attend to like during the encoder, it can attend to all the different other visual embeddings in the image. So here is a very interesting thing. So to train this, so we're gonna end up with such a like gigantic summation of all the like loss terms. So which is pretty kind of annoying here. So is there a way that we can actually like smartly kind of optimize these objective while just achieving like the good result on both reconstruction and sort of understanding? So here is first is the detail of how we make things work. So the first observation is that we observe that the VIT here for the encoder and the generator here are memory efficient because we have so many kind of tricks for making transformer memory efficient. For example, flash attention, like selective gradient checkpoint, etc. But for the CNNs, which is used in the perceptual loss and the discriminator for the GAN loss, these CNNs are actually not very memory efficient. So here is a plot of the memory consumption with respect to the batch size. So we see here that actually more than 60 to 70% of the memory is consumed by the perceptual loss and the GAN loss part. And we have another observation or like sort of like assumption, which we don't have like 100% evidence to say it is true, but we can say like it's probably true. So understanding does not require like perfect reconstruction. So there's actually some evidence about it. For example, MAE, they just use a very lightweighted decoder, and then they can sort of learn the representation very well. And even if we use some sort of more advanced, for example, diffusion head or like Gaussian splatting head on top of that, it does show a lot of like improvement on the reconstruction, but this reconstruction in return doesn't bring a lot of gain on the image understanding. That's why in this case, we sort of like separate the perceptual term and GAN term in the second stage. While in the first stage, we only optimize a combination of the QLIP loss and the reconstruction loss, which is the MSE loss. And in the second stage, we can further like enhance the sort of the reconstruction quality by introducing additional perceptual loss or like GAN loss term. And in this case, because the batch size that is available for each of the iteration is going to be reduced because of the introduction of the perceptual term and the GAN term. So we simply just freeze the visual encoder and drop the text encoder so that actually the QLIP term is gone in the second stage. And we can actually show that during the second stage of this reconstruction, basically we actually kind of can bring back a lot of the details of the images. And once we figure out this two-stage training pipeline, there's another issue, which is how to balance the loss between the contrastive pre-training loss and the MSE loss. So there's actually some previous work that handle this, because the reason here is that if we have like a histogram of the gradients from the two losses, actually we see a very huge difference. For example, the alignment loss with respect to the last layer of these two. So we basically take the last layer, the last common layer of these two losses, and then compute a gradient with respect to this kind of layer, and see the gradient magnitude. Actually, we see the difference of this magnitude can be in the order like 2 orders of magnitude. So in QGAN, actually, they have an adaptive weighted term to tune this. But this is kind of expensive in our case, because the last common layer in VQGAN is simply the last layer of the decoder. While in the QLIP, the last common layer by these two losses is way much farther than the last layer of the decoder. Actually, it's the last layer of the encoder. So computing these like adaptive loss weight is actually very expensive when we are like training it in the real world. So instead, we basically just have an approximation, which is we train the two models with like two losses separately. And then we get the final loss value. And then we just use the inverse of these two loss values to be the loss weight, just to like sort of approximate such loss weight. And it just works. And that's why we don't use this adaptive weighting anymore. And with this kind of quantization, so now we can just implement it into a unified multimodal model. So we simply just start from Llama 3. And we sort of augment the vocabulary such that we can initialize the vocabulary because now we have the like tokenizer for the visual part, and we just convert the patches into the indices using this visual tokenizer, and we have to initialize the embedding for each of the visual tokenizer. And then the way that we initialize this is just use the average of the initialization from the Llama 3 for the text vocabulary. So this will actually improve the training. And for the data mixing, basically, we just mix the text data and then the image text pair data. So here is some like key result that we can just quickly go through. So first of all, we show the state-of-the-art reconstruction FID result, and then understanding performance, which is measured by the zero-shot accuracy in 2 axes. So this is never achieved by previous method. And we also show the size of the bottleneck here using the size of the squares here. And we actually show that QLIP is significantly smaller in terms of the size of the bottleneck. And this understanding performance also generalized to VLM. So for example, Lava 1.5. And here is the generation result where we show that using this text-aligned visual tokenizer, it actually yields a much better like text-to-image quality, for example, on Gen eval and then DPG bench. And finally, we also showcase that with this visual quantization, we can actually train a chameleon-like model without even need to like train everything from scratch. We basically just initialize from Llama 3. And this is way much more efficient than what Chameleon did because they actually trained everything from scratch on the like text and then image data. And it also showed a comparable result on all the text-only benchmark and image-to-text benchmark and text-to-image benchmark. And that's pretty much of it. Yeah.
Thanks. So we have a quick kind of 5-minute Q&A session, and then we move on to the next one. And then we are also going to have a discussion session at the end. So ample time for that. So we can also keep more fundamental philosophical question there as well. I don't know.
Yeah,
better split.
Sounds good. Yeah.
But yeah, please go ahead if any of you have any question. Otherwise, I also have some questions, but yeah, we'll see if there's any other question. So maybe one question from my side is whether you have so the final figure that we're taking a look here. So are these kind of representing the understanding and generation aspects of this model as well?
Yes, that's a good point. So I think here we are showing, so for generation, we have like text-only benchmark. For example, all these axes that is covered by the blue curves, they are like benchmarks on the text understanding or like generation, because actually it's just like regular natural language benchmarks. And for the generation, for the image, basically we are looking at text to image. So we actually show the performance on the generation on Coco 30K in terms of like clip score and the generation FID. And for the I think for the understanding capability for the visual side, we are looking at image to text, which is like image captioning. So like we're just thinking of like caption can be like as a way of representing the understanding capability of images by just talking about what's happening in the image, right? By just captioning. And here we are like showcasing the performance on MS Coco caption in terms of CIDR score and then Meteor and Blue score.
Yeah, I mean, this is super interesting and super nice result. So I see that for MS Coco Blue score, none of the previous kind of approaches are doing a good job here, and you're kind of doing better. So can you maybe explain what this task is exactly measuring? Is that, I think this is still captioning, right?
Yeah, right. I think so for captioning, what we do is we in the data mixture stage, we use the data from the CC 12 million and all the images from the segment anything data set. And what we do instead is we basically use like a QN2VL model to like pre-caption all the images. So basically, to sort of generate such image text pairs, and based on that, we are like training the model on top of these image text captions. That's why I think it probably comes from the capability that we are sort of distilling the captioning capability from the QN to VL. I think that sort of explains why the caption result can be actually better than some of the specialized zero-shot captioning model here. Yeah.
So yeah, I think generally this is a very interesting insight that for languages, we are doing generation and understanding at the same time. But for images, maybe just out of curiosity, what's the reason why the vision had to be kind of developed in this way, in a separate way in the first place?
Yeah, I think that's a very good question. My answer would be like the generation for visual will just be very complicated because it's in such a high dimension, and for languages, like all the words are sort of like in a very abstract and then like condensed way. While for visuals, basically the way that we perceive is actually in a very kind of raw, kind of natural format. While if we want to also generate things in such a way, then we basically have to have a really like complicated model to sort of model such thing in a really high dimension. So I guess probably it's also the thing for human, like we are really good at perceiving like the word, but it's really hard for like a common people to draw something really good. We probably can just do get sketch or something like that. So even for human, like doing some sort of image generation in terms of like drawing is really hard, right? So I think that's probably the reason, like the hyperdimensionality, the complexity might be the reason that we cannot do like generation very well, and that's the reason we cannot do like generation and understanding together very well. So like, for example, if we look at the state of the art sort of image generation model, they are kind of like good at like generating some like portrait images, but once it goes to a really complicated scenario, for example, if there are like if you want the model to sort of generate a scenario with like 20 or even 30 objects, then it's really kind of cannot know like it cannot like do everything properly. So it will sometimes just like break. So that actually, but for on the other hand, so if we are like doing understanding task, for example, as detection as an example, we can pretty well like sort of detect like 1,000 object in an image, like using like face detection, for example, or like just like a general object detection, and then it can also do pretty well on like maybe 100 objects in one single image. So that's the reason, I guess. So probably there's still a gap between these two models separately, and that's probably also the reason why it's really hard to sort of like building kind of a unified model from the first principle. Yeah.
Yeah, thanks. I mean, yeah, maybe that was a little bit too fundamental question for now, because I was not trying to ask that. But yeah, but thanks a lot for the answers already, and maybe we can move on to the next speaker and then come back to more discussion. That's all right. So we have the next speaker, Dominik, who's going to present about the paper called It's a Blind Match Towards Vision Language Correspondence Without Parallel Data. Quite interesting. So please, if you're ready, please go ahead. Thank
Okay,
you.
can you see my screen?
Yes, I do.
Great. Okay, let me. Okay, so yeah, I'm Dominik, and I'm presenting our CPR paper from this year. I want to show you today that one can get some vision language correspondence already without any paired data. Given embeddings from an arbitrary vision model and language model, the embedding spaces are generally completely different, right? So they are probably of different dimensionality. If you have Dynamo V2, you have something like 1,500 dimensionality, and for some of the sentence transformer models, you have like 700 dimensions or any other. So you don't really have them to be aligned. So what can we use instead? And for this, we mainly build on top of the Platonic representation hypothesis. So I will first go over the Platonic representation hypothesis. So given different objects in the real world, both images and text are abstractions of the same underlying world. Using a pre-trained text encoder and image encoder, these abstractions can be mapped to two different embedding spaces. What the Platonic representation hypothesis mainly does is to evaluate how close the pairwise distances are in both embedding spaces. So pretty much whether the cat is closer to the dog than to the airplane in both spaces. And they find that with increasing compute and data, the pairwise similarity becomes more aligned. So this means that for large enough data and model, the cat is probably closer to the dog than to the airplane in both the image and the text embedding space. So the pairwise distances become more similar between vision and language models when you have more data and larger models. So how can we use that to find correspondences now? So assume we have now unpaired data, and we try to align these two modalities and these two embeddings. Then we try to align the pairwise distances as good as possible by permuting the text embeddings. So the distances between the text embeddings should be as close as possible to the distances in the vision space. We formulate this as an optimization problem and introduce an heuristic solver called factorized hung ground. Given our heuristic solver, our work shows that it is, or it could indeed be feasible to find matches between vision and language without any paired data, just using these pairwise distances. Okay, so wait, the Platonic representation hypothesis only showed that pairwise distances become more similar for larger models and datasets, but it didn't show that the alignment is a good metric for finding permutations or finding shuffling in the data. So is this a really suitable metric to optimize for? And for this, we just did a basic experiment on COCO captions. So this is an image caption data set, and we evaluate different alignment metrics, for example, mutual KNN that was also used in the Platonic representation hypothesis, and the centered kernel alignment. And in the next step, we shuffle some of these text embeddings. So we shuffle the text captions, so they don't align with the images. And for a specific amount of shuffling, we shuffle this amount of text captions. So we have like non-aligning pairs in there. And we compute the alignment for these non-perfect matchings. Yeah? And we repeat this experiment for a couple of random seeds. What we observe is that the similarity strictly monotonically decreases. So this means that the pairwise distances between image embeddings that are most similar to the corresponding language embeddings also have the highest alignment. So the alignment is best, or the similarity between these pairwise distances is best when you don't shuffle the embeddings. So now let's dive into the optimization problem next that we want to optimize for. So here we want to maximize the similarity such that we have the best correspondences at the end. So we're given some vision distance matrices. So for example, the distance between the cat and the dog, or the cat and the airplane in the vision space, and also in the language space. And we optimize over permutation matrices. So they are one, or they have an element of one, if we try to, if we have a correspondence of this vision embedding to another language embedding. And we only take into account those pairs where we have this correspondence. So where the ijth value and the kth value is 1 in our permutation matrix. Altogether, this objective is a quadratic function of the permutation matrices and an instance of a quadratic assignment problem. To solve this problem, we introduce our custom solver that we call factorized hung ground. And this is pretty much an extension of a dual quadratic assignment heuristic from operations research, where we change that we find good primal solutions during the optimization, and we made it more memory efficient. And finally, we also made it a little bit faster by using better linear assignment solvers in the inner loop. In our paper, we show that our solvers outperform previous solvers in both small and larger scale problems. For details, you can also have a look in our paper. So now the main question arises, how well this matching really works in practice. And first of all, we will have a look at small scale problems, so Cypher 10 and Cynic 10. Cynic 10 is pretty much Cypher 10, but with larger resolution images from ImageNet. but with the same 10 classes. And for each class, we compute a representative vision embedding and a representative language embedding. And so we have like 10 language embeddings, 10 vision embeddings, and we try to find a one-to-one matching between those. We observe that most of these models achieve a non-trivial accuracy, so an accuracy larger than the 10% accuracy of just random permuting them. So these pairwise systems are already enough to find correspondences between some of these classes, just by looking at these pairwise systems in both spaces. And especially the DynaV2 models, so on the right-hand side here in dark blue, are like really excelling and have the highest accuracy of all these models, and therefore embed the pairwise similarities very similar to these language models for most of these classes. Okay, so let's have a look at some larger data sets. So here we have ImageNet 100 and Cypher 100. So we have a set of 100 embeddings for the language embeddings and for the vision embeddings. And for 100 classes on the right-hand side of the plot, we can see that for the whole data set, so we're including all 100 classes, the matching accuracy is only marginally better than random. So does it work at all? And this only shows one part of the story, because when one is like iteratively leaving out some of these classes that are not well aligned, we observe that many of these classes, like 20 to 40 classes, depending on the data set and the model, can already be matched with very high accuracy. So there are some classes, like 20 to 40 classes, that have very similar distances in both spaces, both in the visual space and in the language space. So, however, the steep drop both here on ImageNet 100 and on Cypher 100 shows that once you include certain classes, the whole matching is disrupted. So these classes probably have very different distances to all of these other objects. So are probably represented very differently in these two modalities. So moreover, we also see that supervised models usually perform a little bit better than self-supervised models, especially on these very fine-grained classes. Okay, so this experiment again uses like 100 representative vision embeddings and 100 representative language embeddings, but in practice we usually have multiple vision embeddings, like one vision embedding usually for one image or so. So we can also directly extend this, for example, to image classification to perform unsupervised image classification. How can we do this? So in image classification, we first have a set of classes, and for each of these classes, we have a set of images. We now assume that we don't have any supervision of this. So we don't have any paired data, we don't have labels for these images, we just have a set of images and a set of class labels. And what we can do is we can cluster these image embeddings of a self-supervised model, for example, like DynaV2, using something like k-means. We can compute the representation for each of these clusters. For example, these could be the centroids and k-means. And we can compute these pairwise distances between our centroids, like our pseudo labels, and our ground truth class labels. And then we can apply our matching to find correspondences between these two. So in the end, we have that each of these images corresponds to one cluster and therefore to one of these class labels. So we have a classification in the end. So how well does this work in practice? So again, on Cypher 10, we can see that we have with unimodal vision and language models, like a sentence transformer model, only trained on text, and DynaV2 only trained on images, we already get like over 50% accuracy. Like over 50% of these classes or these images are correctly assigned to this other class just without any supervision, just by using these pairwise distances. So this is very far from the supervised state of the art, but I think it's quite interesting, and it's the first instance of fully unsupervised image classification. And I think it's really interesting that these pairwise distances are already enough information to do that. So the main takeaway message is that vision embeddings and language embeddings can already be matched without any supervision for some concepts, and this is made possible by similarities in the pairwise distances in both spaces. So yeah, thank you for your attention, and I'm looking forward to your questions.
Thank you for the great talk. Any question from anyone? So one question from me. So you're applying permutations on the axis, right, of the space. But but I think maybe you have also considered linear transformations instead of permutations. Maybe it's a little bit easier because to do linear transformation, because that's more continuous optimization as well. Do you have any thoughts on that?
Yeah, so I think the main problem with doing some linear transformations is that we don't have any ground truth. Yeah, because we don't have any paired data, like we don't use any paired data in our task. We can't really have a target for all linear transformations, so it's pretty hard to optimize it. Yeah. What we did try was a combination of both. Yeah, we tried to find like which of these language embeddings corresponds to which of vision embeddings. Yeah. And then we can match it in the other space, yeah, by a linear transformation, for example.
Mm-hmm. So I guess your point is that for learning linear transformation, there's a lot more parameters to learn, and essentially the distance structure is only as much as quadratic to the number of classes here, right? Is that right?
So we could directly match or directly map one of these classes in like of the vision embeddings into the classes or in the embeddings of the language space. So I think that's not really the problem, because this is just dependent, like this linear transformation is just dependent on the dimensionality of both spaces. But in the end, what's problematic is that we don't assume any paired data and any supervision. So we have 10 vectors in one space, we have 10 vectors in the other space. And what is our target to our linear transformation? So we don't know. Sorry?
The same objective as in one of the slides that you had. So instead of just considering the set of permutations, can you just increase the search space to linear transformations?
So we have a permutation and a linear transformation. That's what you mean. Yeah.
Yeah.
We could do this, and especially like isometric transformations would be quite meaningful, because then we would keep the distances as they are.
Yeah.
We also played around with this a little bit. So like doing this permutation in text space, and then trying to apply a linear transformation to this text space, or the other way around, and directly trying to align this. However, the performance was a little bit worse. So we didn't put it in the paper because the performance was a little bit worse. But yeah, we didn't really see any improvements by learning a linear transformation in addition to the permutation. Yeah. Also, I think the main problem with this is we've seen that usually local optima for this optimization problem don't lead to meaningful matches. So then just some classes are matched to other classes. So for example, also just using optimal transport doesn't really lead to any meaningful matches in the end. Yeah. So one really needs this global optimum. And once you take some linear transformations that just lead to some local optimum, it's a little bit problematic to get this global optimum in the end. And I think if we could get the global optimum, I think also with linear transformations, it could work. Yeah.
So, okay, thank you for the answers. Maybe we can straight jump into the discussion, and there is a raised hand from you. Please go ahead.
Yeah, thank you for the talk. I actually have a question. So how fast is the solver? Do you have any like analysis on the with respect to the complexity? Because I guess there's like a number of the classes and yeah, and then the samples per class, right? So all of these, do you have any observation on that?
Yeah, so the complexity is quite bad. So like solving quadratic assignment problems in general is NP hard. So it's an exponential runtime to solve it optimal. Our heuristic usually finds the global optimum for like most of the problems we've seen, especially for like smaller scale problems. And that one has a complexity of O to the power, like O of n to the power of 5. So where n is the number of classes. So it's pretty difficult to really scale to extremely large scale problems. That's also why we stick to problems of size 100 at most, and don't go much larger, for example, to ImageNet or something like that, because it's still a very, very strong limitation to do this computation. Yeah.
Yes, and then yes, thank you. So another follow-up is I think you also you just show the matching accuracy with respect to the problem size, like which is like basically the number of classes, and then you just said like the matching accuracy dropped significantly at around like 20 to 40 classes. And have you done anything like just I don't know, like enumerate all kind of like combination of these 20 classes out of these 100 classes to see if the problem is really from like a specific subset of these classes, or like is there any like pattern of like, or like for any combination of these like 20 class subset, it will just like contribute to the like performance drop. That's the question.
Yeah, so for this one, we chose classes that are already well aligned. So we choose 20 classes that are well aligned, and this usually also corresponds to classes that can be matched quite well in the end. Like these are usually the classes that can be matched best, and then to the classes that can be worst in the end.
I see.
Yeah, but for this, we've also seen that very fine-grained problems, also a very small scale, usually have quite a big problem with these pairwise distances. So, for example, if you have some different dog breeds and you try to match them to like from vision models and language models, these representations don't align at all. So that's currently like I think a big limitation, and we don't really have good pairwise distances in both spaces, or very aligned pairwise distances. Yeah.
I see. Yes. That's a great answer. Yes, basically like the number of classes already sort of like indicates the difficulty of like doing the matching, right? Is that correct? So basically like you're picking the classes that is easier to like kind of match at the very first place, right?
Yeah, exactly. Yeah.
Okay.
So
cool. That makes sense.
Yeah.
Yeah.
Okay. Thank you. Yeah.
Good. So maybe following up on that, maybe one question that I had was you're only so the kind of graph you're building for each modality is the on a per class basis, right? So you don't go into kind of instance level and take a look at the distance graph within the class across different instances.
Yeah. Like in some preliminary experiments, we've also done something similar. So the optimization problem also gets a little worse, but I think one can also live with like worse matchings then, because just like assigning one instance wrongly is not as bad as assigning a whole class wrongly. So so there are also some methods that can solve this more or less well. However, just clustering and then matching, like in this unsupervised classification setting, usually worked a little bit better than that. So just clustering vision embeddings and then matching is already relatively good. And I think the performance was very similar, but yeah, it's much easier.
So maybe I'm not sure if this is a valid thought, but if you go into the instance level kind of depth, then instead of taking the full kind of distance graph among the instances, do you think there's a possibility to just count the number of instances per cluster or something? Because maybe in the data set, there'll be different number of instances per class. I mean, that gives you quite some information about which cluster correspond to which cluster in the other dimension. Although that feels a little bit like cheating, right?
I think that's again some kind of supervision, right? If you already know for this class we have this many samples, but I think it could help. Yeah, if you have this information, you can like constrain your permutation matrix, or your not permutation matrix at that point then. But you can constrain that matrix to be exactly this number of classes for each of these. This will definitely improve the optimization problem if you have this knowledge. Yeah.
Yeah, I guess the main objective is not to solve this problem, but I guess to kind of understand better the structure of the embedding spaces. So
exactly. So I think no one really or should use this to do any kind of like image classification. It's more just to show that like vision and language models like learn some common knowledge that is embedded in these pairwise distances, and that we can use this, and they are quite similar between text and vision models for some of these classes. Yeah, so I think that's the main message from that. So to say, yeah.
Yeah. So maybe after this, coming back to the talk by you, if I may ask further questions there. I'm still kind of wrapping my head around. I think this is a very interesting, curious problem to tackle. What happens if you train the generation and understanding at the same time in a single network? Do you think there's any kind of, so to say, emergent behavior that goes beyond just doing understanding and generation well? I'm not sure if the question is super clear.
Yeah, I think I probably need some more kind of hint to answer this. Yeah.
Yeah, so I mean, from a motivation perspective, I think the starting point is very interesting. I guess my question is, do you see any other practical benefits beyond the fact that this is a kind of a generalist model, which is doing generation tasks well, like individual generation tasks well, and individual recognition tasks well? But is there maybe something else?
Yeah, I think there's some sort of motivation to support this. So basically, like when we are doing generation right now, we see a very kind of frequent failure cases where the image that is generated cannot follow the extraction very well. So if the model, the underlying model has like better understanding for the image or like the instruction, then basically it can generate things much better. For example, we know for example, like we know like generation model cannot do counting very well, but actually the understanding model then themselves are not like very good at counting, right? It can do like pretty well at detection, like single objects. But if we just want to ask the model to say like how many like persons are there in the image, and then it can probably fail if we are just not like asking them to detect the human faces, right? So I think these things are kind of like intertwined with each other. So maybe if we like solving this in a holistic way, maybe it can actually help benefit each other. And the other way is like what like sort of like that also relevant to like generation. So like for understanding, sorry. So for understanding, we like classification is one sort of understanding, like one kind of global understanding, and we also want to understand the image more kind of in a finer grain. For example, like instance segmentation or like semantic segmentation. These are also sort of like conventionally classified as a like understanding problem, right? But all of these once we are like doing this detection or like segmentation task, it might be better if the model is good at generation. For example, it might make the mask sort of more kind of crispy, right? Or sort of things, something like that. So I'm thinking like from a very high level. So uh, eventually we probably need to like think of these two problems in a like a unified way. So, but I feel like there's still a lot of like open questions, like how we're gonna like combine these two, right? So, and then like how we're gonna train this model, all sort of things are like very kind of open-ended. Yeah.
Yeah, thanks. So we are also working a little bit on the problem of kind of turning diffusion models into classifiers, even zero-shot classifiers.
Yeah.
Because we thought maybe potentially diffusion models have some of the capabilities which is complementary to usual QLIP models, for example.
Yeah.
For example, we thought maybe diffusion models are better at compositional generalization because they can compose, right? By definition, some new stuff. Although eventually we also found that diffusion models are not so good at composing something new in a precise way. Yeah, so the basic message is I kind of agree that maybe these two models have kind of non-overlapping set of capabilities, and by combining them together in a single kind of optimization, single training session, maybe all of these capabilities are kind of complementing each other.
Yeah, I think so for diffusion model, actually, I think there's some work that shows like diffusion model can like show some like capability for like doing correspondence, which is something like Dino, right?
Yeah.
So and then they also like there's a paper like show like these like diffusions embeddings actually like sort of complementary with Dino. So so they actually it's very interesting. And then for diffusion, I think there's like a very recent like REPA sort of style model that they sort of inject these kind of clip embedding or like Dino embedding to align when you are like doing the diffusion training. So it also like improve the like the generation quality. So so I think so like because I feel like these like separate models are like trained from like a separate objective, and but like our visual systems are like designed in a way like we are like just learning from everything like from our previous experience like by perceiving. And so like a single objective is might not be like the ultimate the optimal way for like all these kind of different like perceptual tasks. So I think like from this optimization kind of high level like perspective, I feel like adding these like different objectives might also be something really interesting to like improve the capability of these perception models. Yeah.
Yeah, I agree, and that's very interesting insight. Do you think in some way this kind of line of work could eventually lead to some sort of reasoning as well, potentially?
Yeah, that's also a very interesting question, and I'm also looking at it. But I feel like right now reasoning is kind of like most of the reasoning is still handled by the language interface.
That's right.
Yeah, so like everything is like sort of like converted to the text tokens as soon as possible, right? And then so that the RLH of models can actually like operating on top of that and then doing some sort of reflection and then like deep thinking or whatsoever. Um, yeah, but like I don't know, but I feel like there has to be some way of like, okay, you do some sort of thinking, and then probably you have to like go back to the visual again and then sort of do a little bit like think back. Like you don't actually want to just do think like deep think on the text itself. So because it's just too abstract, right? So it loses a lot of like the visual details or sort of the things. And then it might be the case that your vision system is wrong at the very first place, and then your entire reason might also just be wrong. So you have to sort of like go back and then to look at your original image and then figure out if it's the reasoning step until right now is legit, or like you have to like do it again or something like that. So it's like this reflection back to the visual part. I feel like this is something like it's lacking right now. Yeah.
Yeah. Or yeah, exactly. Maybe it could be thought of as some sort of a taking action in the space as well and having a word model as well. So
Yeah.
by doing generation, you kind of can do some fictitious changes in the word and
yeah, like manipulate the scenario a little bit and then see what's the consequence would be, and then just do this kind of guessing, right? Yeah. Okay. I think that's a very interesting direction to explore. Yeah.
Yeah. Very interesting. Yeah. And that actually seems to open up different possibilities to trickle down the advances in language models in the vision part.
Yeah, exactly. Agree. Totally agree. Yeah.
Interesting. So we have some more time. So maybe if there's no kind of further questions,
yeah, I actually have a follow-up question for Dominik. So
sure.
for the alignment problem, yeah, I think So right now, my understanding is like all this analysis is on like Euclidean space. Like we're measuring like just the L2 distance. So, what's your thought on like and then I think the real interesting thing is like once we are doing the matching, it goes bad when we go to like finer grained classes, right? So, but these kind of like hierarchy for the classes for the Euclidean space is actually very like not kind of intuitive from my understanding. So I think there's some work on like hyperbolic space, right? And do you have any thoughts on that? And then like, or is there like maybe there's, or you already have some preliminary result and then you probably want to show or like something like that. Any kind of thoughts on that? Yeah.
Yeah, so to be honest, I think it's a really good idea. So like we've also thought about it. We haven't found a lot of models trained on hyperbolic like space, yeah. I think, but to be honest, like we haven't focused on this too much. But I think it could be quite interesting, especially for larger problems, because we have this like hierarchical structure in the hyperbolic space then. So it could maybe improve our matching problem a lot. So yeah, I think it's definitely a very promising future direction. Yeah.
Yeah, because I think for this hyperbolic embedding, they didn't show a much improvement on just like performance wise, but like I think it never sort of like it's sort of like comparable. That's why like people more like sort of like because L2 is just like simpler to like calculate and then like more memory efficient, for example, and then they just stay with L2. But like if there's like a more kind of like a nice property on this like hyperbolic space, and then with the similar performance, people might kind of switch to like the other way around. Yeah, I guess.
Yeah, definitely. But to be honest, I haven't seen something like DynaV2 in the hyperbolic space yet. So
yeah,
I think
there's like a clip on the hyperbolic space. Like they
yeah,
do like
maybe we should do some
contrastive
experiments
on
with
that
that.
space. Yeah.
So maybe to drop one idea here, hyperbolic space, as far as I have experienced, is capable of identifying sort of the root node. It's kind of a tree kind of structure, right? So at the center is going to be root nodes there, and then there's going to be like children of the root node, and then it goes hierarchical, right? So I think by training in a hyperbolic space, you can identify this kind of tree structure better. And once we have kind of a tree structure instead of just a random kind of unstructured graph of distances, maybe that's more conducive to doing the matching later on, because maybe the root is kind of matching to another root. Maybe it really just boils down to kind of how to rotate the space. Yeah, although you're still doing some sort of rotating using permutation, but maybe there's more regularity in the space, and the burden for doing the matching is a little bit less in this space.
Yeah, it would probably already help to only match the course classes, because that works quite well. And you don't have to care that much about the fine classes.
Basically you can just sort of decompose the optimization into multiple steps, like just do alignment on the roots and then like go to the leaves like from one root, right? So something like that.
So yeah, I guess we have to wrap this up because we also move on to the next session. But maybe Saber, are you here? Or
yes, I'm here.
I also want to kind of emphasize that please, we have some feedback form here on the right side to me.
I'm just putting it in the chat then.
Exactly, yeah. So Saber is sharing the form for doing the feedback. We're on an early stage for this session, and we want to get your feedback to improve continuously on the next session. So your feedback is very, very important in serving you better next time. So please, please take a little bit of time to kind of give us feedback. Anything else that we have to share, Saber?
I don't think so. Yeah, you covered all.
All right, so it's an abrupt end to the session a little bit, but I wish to thank Dominik and Yue again for presenting their work and making a very good conversation afterwards. So wish to keep in touch. in the future.